not so much later, it was discovered that there is a west drift of the declination, and this was not so easy to explain with the Lodestone hypothesis, and the discovery of the reversals of the geomagnetic field brought the Lodestone theory finally in trouble. About 100 years ago, 101 years ago, George Ellery Hale discovered strong magnetic fields in sunspots. More precisely, he interpreted the line splitting in the light coming from sunspots as Zeeman effect, and the existence of strong magnetic fields in this sunspots. We know now that there's also a general magnetic field, and that there are cycles of sunspots, and that they are closely correlated with the oscillations of the general solar magnetic field. It was, interestingly enough, not the magnetic field of the Earth, but the magnetic field discovered at the Sun, which brought Larmor in 1919 to an idea on how these magnetic fields could be explained. There's a famous one-page paper with this title, and that he proposes there that the magnetic fields in the Sun, in sunspots, are due to electric currents which are generated and maintained after the pattern of a self-exciting dynamo. He mentioned in this short paper also the Earth. If there would be, it was not clear at this time, liquid parts of the Earth's core, then the same could happen in the Earth. Okay, self-exciting dynamo. It was invented. It's not clear to say who invented it really. I think these developments, the Samuel von Siemens and Wheatstone, were independent from each other, but with nearly the same result. And there are also other people who had ideas like Siemens. That means take a dynamo machine with permanent magnets and replace the permanent magnets by electromagnets. And then it should work. So you understand the principle best when you consider a disk dynamo. It means let a metallic disk rotate, assume a magnetic field. If you then connect the rim of this disk by lighting contacts over a wire with the axis, a current will flow because there is a potential difference here, and you can now wind this wire in a way that it just reproduces the original magnetic field. And if you then have a arbitrarily small magnetic field at the beginning and you rotate sufficiently fast, then you will have self-excitation. That is the idea of the self-exciting dynamo. An engineer would say, okay, this is a circuit in which I have a inductivity and a resistance, and the voltage at the voltage at the inductivity and the voltage at the resistance. Sum, of course, is equal to the time derivative of the magnetic flux through this coil, and the magnetic flux on the other hand is connected with the electric current. So you have this simple first order ordinary differential equation which you can solve in this way, and you see if the resistance is too large, then you have always decay. But if this quantity omega star, which is proportional to the angular velocity of the disk, is sufficiently large, this becomes negative, and you have growing solutions, and that is the dynamo. Okay. But in bodies like the Earth or the Sun, you have no isolated wires which you can wind in a way that just original magnetic field is reproduced by these currents. You have a continuous medium, and you have to write down the induction equation for the magnetic field and proper boundary conditions. And if this term is missing, it is clear that magnetic fields decay. You can estimate the relative importance of this compared with this by the magnetic Reynolds number, the characteristic velocity, characteristic length, and eta, the magnetic diffusivity. It means 1 over mu permeability and sigma conductivity. Yeah, the influence of this term can be measured by the Reynolds number, and dynamo can only be expected for a sufficiently large Reynolds number, sufficiently large influence of this term. We define the dynamo so that the magnetic field doesn't vanish when time goes to infinity, and the necessary condition, necessary, not the sufficient condition, is that the magnetic Reynolds number is larger than the critical value, which, roughly speaking, is of the order of unity, but in fact it is always higher. I said it is a necessary condition, by far not sufficient. There were many attempts to construct dynamos, which were not successful. And in 1934, as a result of many not successful attempts, Cowling proved the theorem that it is impossible to have a dynamo with an axisymmetric magnetic field. Whenever a magnetic field is axisymmetric, say the Earth's field with respect to the rotation axis, but not only with respect to the rotation axis. If you can find any axis about which the magnetic field is symmetric, then this field cannot be maintained by a dynamo. And there are also theorems which concern fluid motion and so on. And then later, 58, the Cowling theory was 34, and the idea of Romer was 99. So much later, Herzenberg, at this time in Copenhagen, constructed a working example of a dynamo. He took a sphere, the idea, theoretical construction, a sphere of conducting material at rest, except in two smaller spherical regions which rotate like rigid bodies. And if they rotate fast enough, and there is the right relation between the axis, the position of the axis, you get indeed self-excitation of magnetic fields. This is usually considered as the first existence proof of a homogeneous dynamo. Homogeneous means in a homogeneous or more or less homogeneous medium where we have no isolated wires. Another interesting example was proposed by Roberts, by Glyn Roberts, it's not the famous Paul Roberts. Flow pattern, periodic in say X and Y, and independent of Z, can act as a dynamo. That means if you have a small seed field, this field will grow. However, the magnetic field must have, in contrast to the flow, a Z dependence. Otherwise, it would be forbidden to have a dynamo by a theorem similar to Cowling's theory. And another interesting proposal was by Ponomarenko in '73. Again, infinitely extended conducting medium at rest. except in an infinite cylinder, which is in contact with the other medium, and which rotates omega and moves in axial direction. Then you have, or can have, under certain conditions, magnetic fields in the form of waves, of traveling waves. Okay. But all these ideas are not very helpful if you think of magnetic fields of the Earth, of the Sun, or of other cosmical bodies. And the breakdown in this respect came with the mean field theory. So you have in such bodies complex flow fields, and it makes sense to split them into mean parts, defined by a reasonable averaging procedure, and smooth in space and time, and fluctuations. And the same happens then with the magnetic field. And if you average the original induction equation, you get an induction equation for the mean magnetic field, which formally agrees with the original induction equation, except that you have here an additional electromotive force, which is due to the fluctuations of the velocity and the magnetic field. And okay, it's only repeated. If you have helical fluctuating motions, then you have at least a part of this electromotive force, which is proportional to constant alpha times the magnetic field. It is quite different from this electromotive force. It has no component in the direction of the average. And this now has a component in the direction of the average, and so you cannot prove, for example, Cowling's theorem, although it is connected with the assumption that the electromotive force has this form. And so here opens the possibility to have to construct dynamo models for cosmical bodies which indeed reflect essential features of real dynamos, and this led to the conclusion that dynamo is really a basic phenomenon in the universe. I said helical turbulence. Consider as a simple example homogeneous isotropic turbulence. It can be non-helical. Then if you reflect the velocity field at a point, all averages constructed with the reflected velocity field are the same as with the original velocity field. But if you it is possible that they are not the same. Consider a screw-like motion, and you know if you reflect a right-handed screw, considered in a mirror, it turns into a left-handed screw. And if this is of importance for the averages, we have a known mirror-symmetric turbulence. In this case, alpha takes this form. There's some weight function which we have not discussed here, and here is u curl u, but the two u's taken at different points in space and time. We will come back to this later. This is the simplest mean field induction effect there. Okay. I spoke about magnetic field of the Earth, and the solar magnetic field. You all know that in between we know about much more fields in the magnetic fields in the cosmos, with magnitudes reaching from 10 to minus 9 Tesla to 10 to 11 Tesla, 10 to 50 goes, and so we have many objects which require an explanation for their magnetic fields. So far, I said I took a velocity field as I considered it as a given, but in real objects we have to take into account that the velocity field is not given, but it is produced in some way, and it is then influenced by the magnetic field. That means it's a momentum ballast. You have the Lorentz force. And you have in addition the induction equation, and here with the view to the Earth, I added buoyancy force, which has something to do with the deviation of the temperature from a given profile, and you have then in addition this equation for this temperature deviation, and this is already a rather complicated system. If you look for dimensionless quantities, which define the solutions you find for the Ekman number responsible for the rotation, here is the Coriolis force, the Radler number, which is responsible for the inset of convection, the Prandtl number, and the magnetic Prandtl number. And if you look, for example, in the Earth's course, or take the values which we know for the Earth's course, you see there are very extreme values of these quantities, and that's why numeric calculations, numerical solutions of these equations are rather complicated. One aspect is you need a Reynolds number, in any case bigger than unity, maybe much bigger than unity, and if you calculate the fluid Reynolds number, the magnetic Reynolds, the fluid Reynolds number, it is connected in this way via the magnetic Prandtl number, which is very small. Since this fluid Reynolds number is very high, and you have in any case turbulence. So this makes these calculations rather complicated. I will not go into details. I will only say this is one of the famous examples of the solution of these equations. It is now more than 10 years old. And let me come back again in view of this full dynamo problem to the disk dynamo. We considered this equation for no. Okay. this equation. If we consider the back reaction of the magnetic field, we have to add, say, the energy balance. So the time derivative of the mechanical energy is what is the rotation, half theta is the inertial momentum omega squared, plus Li squared, half Li squared, is equal to the losses, so the ohmic losses. This is due to friction. And here you have a forcing term. D is angular momentum, which drives the disk. Okay, in the simple case where you have no current and omega is steady, you find that the omega, which we then call omega 0, has just this value. That means the rotation remains on a certain level, which is defined by the forcing, and this quantity is responsible for the energy losses. Then consider only the case, the steady case. You find that you have again here is the critical angular velocity or critical ratio of omega to driving force to the critical omega. You have again the trivial solution, but it's no longer stable. And in addition, you have two non-trivial solutions which are now stable. So that means the system will go into one of these states here. And if you assume that you have originally an imposed magnetic field, the laboratory just the Earth's magnetic field, if you do this experiment in the laboratory, you have to add here the flux of the imposed field, and what you find is this. Even here, before you reach the critical point, you have a small current, and it grows in this way. You have another branch, not connected with this, but connected with an unstable branch in this way. Okay, I wanted to speak about laboratory experiments. If you consider, remember that I said the most important parameter for a dynamo is the magnetic Reynolds number, and a dynamo requires that the magnetic Reynolds number is above a critical value. If you think not on cosmic situations, but laboratory or similar simulations, then it's perhaps reasonable to take a velocity of 1 meter per second and a length of 1 meter. It is already very large. It is no longer an experiment for a laboratory table. And if you take the conductivity or the diffusivity eta of the Earth's core, then you have a modest Reynolds number of 1/3, so no hope to have a dynamo with these dimensions. If you take Mercury, then the eta is a bit higher, and you get a Reynolds number of 1.25, but I already said order of unity is not quite correct. The lowest number we know from models is 17, and in other cases it's higher. No hope to have a dynamo. If you take liquid sodium, sodium is liquid at temperatures above about 100 degrees, situation is a bit better. You have a Reynolds number of 12.5, still not enough for a dynamo, and you must have in mind if these are the characteristic values for the velocity and for the length, then the device must be much larger, so that you have inside this device such quantities. That means you have no one-side form of the cosmic dynamo, which you could realize simply in the laboratory. But we have devices on the Earth's surface, which are larger. These are the liquid sodium circuits of the fast breeder reactors. So these circuits are used to transport the heat produced in the active zone to the periphery, where devices are which transform it in electrical energy and so. And these circuits are really huge, and with these ideas I explained to you about the possibilities of dynamo, you must fear, or you can expect that in such circuits, depending on the geometrical shape of the flow, self-excitation takes place. This would be a catastrophe. If a magnetic field suddenly grows, then the flow is break, and the heat can no longer transport it from the center of the reactor to the periphery, and this would be really a catastrophe. And this was told, my former chief Max Steinbeck told it, or wrote a memorandum to the Soviet Academy of Sciences about this danger. And after that, in '74, was a meeting in the reactor city of Minsk near Moscow, where this danger was discussed. This idea was also independently considered by two British scientists, and between careful measurements have been made when, for example, this reactor was filled with sodium, or investigations were made with the French superphoenix reactor. Okay. An interesting example how findings of the basic research certainly have meaning for very practical things. By the way, the reactor engineers didn't believe this. It took some time until they understood that it is a real danger. Steinbeck used this development for a political argument. He wrote a letter to the president of the Academy of Sciences of the DDR, the Soviet scientists, and proposed dynamo experiments. And his estimates were you need about 10 cubic meters of sodium, and you need volumetric flow rates of more than 10 cubic meters per second. We know now it is a tremendous overestimate. You need much, but not so large numbers. Okay. Read this sentence, but follow what's supported that Kami said or what's this. But laboratory experiments with dynamos are more than a good demonstration of an important principle. We know that in natural dynamos we have very complex interactions between flow and magnetic fields, and we cannot completely simulate them in numerical simulations. It's very important to have experimental results and to confront them with the results of simulations. And what we have experienced in this context is that the interaction of theory and experimental observations is really good, pushes the understanding of dynamic process forward. Okay. If I look which dynamo experiments have been made, first some dynamo-related, not really dynamo experiments. The first one I know took place here in Stockholm, and Leonard took a vessel with sodium and rotated the sodium in a different, produced a differential rotating plate, and then say the axis of the vessel is in that direction. Then we got a rotation rate depending on that, what we call differential rotation, and he observed that an axial field, which was externally applied, produced a toroidal field, a field in phi direction. So this is an interesting idea for dynamos. Next experiment, I explained you the Hertz idea. Lewis and Wilkinson in Newcastle, in Great Britain, replaced the spheres by cylinders, not infinite, but long cylinders, and put them in a block of metal. They took ferromagnetic materials in order to have the magnetic Reynolds number high. Eta, the magnetic diffusivity, is 1 over permeability times conductivity. And if you take materials with a high permeability and they use permeabilities, relative permeabilities up to 200, then you can enlarge in this way the Reynolds number. The trouble is that these ferromagnetic materials always show nonlinear phenomena. And this makes the interpretation of the results very difficult. So they took this house-shaped block of iron, and here are the two cylinders, and indeed they observed that for certain speeds of this rotors, self-excitation took place. They did the same with another kind of steel, and they observed oscillations. By the way, it was found, oscillations were found in the theory of the Hertzenberg dynamo later on too. So it was unexpected at this time, but it was explained later. They made the same experiment with copper, which has a higher conductivity than iron, but has no the relative permeability is equal to 1. And yeah, you see, nothing was observed. No dynamos or Reynolds number was small. Later at another device, this electric iron, they found also irregular behavior with reversals and so. All looked very interesting, but the interpretation was different. So another experiment was made in Riga in 1967 to show or to demonstrate and to investigate the alpha state. They considered two tubes through which liquid sodium was flowing, braided, and if you investigate this arrangement of flows, of velocities, you find that your alpha coefficient should be unequal to 0. That means if you apply an external magnetic field, say in this direction, you should have an electric field in this direction too, and should measure potential difference between here and here. And they indeed measure this potential difference. So here is this potential difference. Here also applied externally applied magnetic fields, and here is a measure for velocity squared, and you see the linear dependence of the voltage on this. Here is the dependence of this voltage for different flow velocities on B, and you see for large B, whatever it means, there are deviations from the linear behavior. It is what now is discussed in Mitri, as quenching of the alpha effect. Okay, and now the Riga really dynamo experiment. Alpha effect is an important element for dynamos, but it is not a dynamo. So, this is the Ponomarenko arrangement. And if you put this velocity field in the induction equation, you find that there can be growing solutions, positive lambda, under certain circumstances. That means for sufficiently low Reynolds numbers. This is the Reynolds number for this motion, and this is the Reynolds number for the axial motion. And you see the smallest possible Reynolds number in this arrangement is 17.7. And this was the reason for choosing this type of flow. Among all possibilities the Riga colleagues discussed, where here's the smallest Reynolds number. It was, of course, difficult to reach high Reynolds numbers, and that's why they designed an experiment after this pattern. They added to this helical motion here a back flow which made the traveling wave or transformed it into a standing wave, which is better for the experiment. And yeah, the experiment was first time carried out not in Riga, it was designed by the Riga colleagues, but in St. Petersburg, at this time Leningrad. And this is a Ponomarenko, a cylinder, 3 meter long. Sodium is fitted in here and goes out here, it's 25 pumps. And here by blades and so on, the Ponomarenko flow is produced. They applied an external magnetic field first and measured the voltage between here and here. Under dynamo conditions, this voltage should go to infinity. And so they registered here 1 over voltage, independence on the Reynolds number, and use and the dynamo should occur at a place where this curve strikes the RM axis and intersects the RM axis. These are the measurements, and when they came close to this point, a very strong vibrations occurred in this device, and the device was destroyed. So these vibrations may indicate that you are close to the dynamo situation, but you have not reached the dynamo. Of course, it was the idea to repeat this experiment, 87 I said, but then came the very unquiet times of the decay of the Soviet Union, and it took a long time that the Riga colleagues, now really in Riga, made a new experiment. This is again the Ponomarenko cylinder, and now it is closed, and this flow is produced by a propeller there, driven by a motor. Here is a calculation of the magnetic field. These are surfaces of constant magnetic field, which should occur here, and this is the full device, the motors which drive the propeller, the tank for liquid sodium. This is again the Ponomarenko dynamo magnetic field calculation, and yeah, and it was in the night from November 10 to 11, 1999, when they made first time the experiment, thinking that now self-expression should be reached. And the device worked, but a few seconds later, sodium came through a seal and produced a little firework, and the device was automatically switched off. And so they measured 14 seconds until this firework took place. They measured a magnetic field by a sensor outside this way. It is essentially the externally applied magnetic field. Of course, our colleagues were very sad about this accident, and it took a few days. Then they analyzed these curves, and they found it is a superposition of the externally applied field and the slowly growing eigenmode of the dynamo. This is the dynamo magnetic field, and you see it grows. So they could say we have found a dynamo, the first dynamo on the, let's say, on the Earth's surface. We assume that there's another dynamo in the Earth's core. So, okay. Only a few days later, the Karlsruhe dynamo experiment was successful. The motivation for this experiment and also the design is completely different. It was really motivated by an idea how the convection inside the Earth looks like. There was a proposal by Busse. You have in the rotating, rapidly rotating Earth convection like this. You have these rolls. It is a consequence of the Taylor-Trautmann theory that you have only small gradients in say z direction, x2 direction, and then you have motions like this. Of course, a complete set independence cannot be because here this cylinders are finite. So, in the experiment, they took an arrangement of 52 such elements, they called spin generators. Each of them had a central channel where sodium was passed through and was surrounded by a helical channel. And so that you have also motion in this direction, or here you have mixed motion in that direction and motion in the x, y plane. And, okay. Let me mention that the idea which is usually described with Busse, you find already in a paper by Gailitis. Here you see the dimension, radius 85 centimeters and height 70 centimeters. 3 pumps were used to drive the sodium through this system of channels. Here you see this dynamo module. These are the tubes which connect the different spin generators. These are the tubes coming from the pumps. Oh, sorry. This dynamo module is here. And all these other things, sodium tanks, the pumps, the cooling system and so, fill a house of 10 meters by 11 meters by 11 meters. Really not a device for the laboratory, it's a laboratory table. Okay. The theory is based on the Roberts dynamo. I already showed you that this flow pattern can be presented in this way, and if you feed it into the induction equation, you find that magnetic fields are possible, which can grow of this type, and you have non-decaying fields, that means a negative B. If this condition is fulfilled, Rm perpendicular is again the magnetic Reynolds number for this motion, Rm parallel for this motion, phi is a function of this Rm perpendicular, which is always smaller than unity, which decays a bit with Rm parallel. And if this is exceeds a certain value, which is given here, then you have a dynamo. A is this dimension, and K is the wave number in z direction. That means the inverse wavelength in z direction. Okay. Let's see. This is nothing new. I show you here only this function phi. You can make a mean field theory of the Roberts dynamo. You have again the induction equation with this additional electron of force. It is equal to alpha, now tensorial alpha times the magnetic field, and we have other terms, so that you have some kind of anisotropic alpha effect. You have no Z component of this electromotive force, and the alphas are just this expression. The theory, there are two branches of the theory. One direct numerical simulations, and the other with mean field theory. In all cases, a Radler spherical was used, and the cylinder, dynamo module, was put into a sphere, and the conductivity here and here and here and here was what you used, so that at the end you treat a cylinder. This is one interesting aspect. First, it was expected that the field produced in this dynamo module is axisymmetric with respect to the axis of the cylinder. Would mean here is the cylinder, this is the axis, and here is our isolines of the toroidal field, and here is the toroidal field. But it turned out that the excitation conditions for non-axisymmetric fields are lower, so they cannot be so easily be represented. This is, say, the XZ plane, the YZ plane, and they will look from above. On the cylinder is a bit more complicated field. It has some staircase structure, and these are the radial components of the field at a certain surface, not really at the outer surface, but the surface inside. If you do mean field theory, then you see that the important parameter is something like the magnetic Reynolds number, but here from with alpha, and it depends on the flow rates through the two channels, the central channel and the helical channel, and this C alpha occurs as an eigenvalue of the equations you have to treat, and here the isolines of C alpha in a VC VH diagram. So at the end we found about 8 for this eigenvalue depending on special conditions, and if, for example, this would be 8, then this would correspond to C alpha equal to 8. Then this would be the region where you have a dynamo, and this is the region where you have no dynamo. The dynamo must decay. The same calculation with a more realistic profile of the flow. Yeah. And here is a part of this BC-BH diagram. So these lines should divide the area into the two parts with dynamo and not dynamo, and this is the result which was found experimentally, which is also close to what is predicted by the theory. And this is interesting here. The flow through the central channel is fixed, and this is the flow through the helical channel, and this should remind you of what I showed you with this dynamo. Just this was observed in many cases. Yeah, okay, this is only what I already showed you. Okay. I didn't speak about saturation, of course, both in the Riga case and in the case of the Karlsruhe. Saturation effects were investigated, and here, not unexpected, you see that if saturation takes place, the profiles of the flows through the channels were deformed, and the profiles are more piston-like, flat, not a parabolic profile without magnetic field, but piston-like profiles. Okay. Yeah, this the third successful experiment done in Cadarache in France with the name BKS Van Karman, the physicist Van Karman, sodium. Van Karman flow is a flow which is produced by two counter-rotating plates in a cylinder, and it looks like this. This is in sodium, and it was expected that here a dynamo takes place. But the French colleagues didn't observe a dynamo with this. They constructed a new, bigger one with more powerful motors, and they also didn't observe it, and they made numerical calculations, and they found if they change in the numerical calculations the boundary conditions at this place, so as would these plates be of ferromagnetic material, then it should work. And they replaced these plates indeed by ferromagnetic materials, and the dynamo started to work. Note that the working fluid is not ferromagnetic. Only these plates are ferromagnetic, which changes the boundary conditions. So it is not as in the case of Lewis and Wilkinson. And it is till now, it was done first time successfully at the end of 2006. It is still now under debate what really happens here. And also interesting aspect is that they observe mainly an axisymmetric field, or at least a strong axisymmetric with respect to this axis component, which cannot occur from motions, axisymmetric motions of that kind. So, other small-scale motions must be important. Mean field effects must be important in this dynamo. Okay. I think I should skip this, and I should simply say there are more experiments under preparations at these places. I have something prepared about these experiments, but I think I should stop here. Time is over. Thank you very much for your attention. Thank you.
Thanks, Karl-Heinz, for bringing us up to date on these very current developments in this field. Questions, please. So the flow rates, you said initially one was thinking 1 meter per second would be, that was the old Steenbeck estimate, would be required.
He said
that was the old estimate, I think.
1 cubic meter,
yes.
10 cubic meter per second.
But before that, I think you said 1 meter per second. Yes, you
it
said
was
1 meter.
The example I made here.
Yes. I think you said 1 meter diameter and 1 meter per second would be still insufficient. So, and you showed us volumetric flow rates of 100 cubic meter, yeah?
Yeah.
Cubic meter per second. That corresponds to very high.
What Steenbeck said was 10 cubic meter per second. And what you have in the, say, Karlsruhe experiment is about 100 cubic meters per hour.
Oh, that's per hour.
You have to divide it by 60.
Yeah. So it's perhaps comparable. Yes, further questions, please. Yeah, maybe we should not let it go on for so long, but it was at least a pleasure for me, at least, to see some of these experiments. I saw the Karlsruhe one, which in the meantime has been dismantled. So it's no longer possible to reproduce that experiment, and of course I also saw the Riga experiment in operation, and I'm looking forward to seeing the Kararash experiment at some point, which I have not had the pleasure yet. But Kararash is of course where they run the where the ITER facility is running. That's why they have so much liquid sodium there.
Yeah, the Riga experiment has not been dismantled. Could be.
Oh yes.
Karlsruhe experiment. Oh.
Yes. Good. Okay, so if there are no further questions, I'm let's thank Karl-Heinz again.